Hello all. Today we are going to look at the subject computational intelligence, and the first and the second module deals with fuzzy logic. So fuzzy logic, these are the contents that we are going to cover, and the first module deals with the first course outcome, that is CO1, which indicates that the student will be able to apply fuzzy logic to handle uncertainty and also solve engineering problems. So as an introduction to fuzzy logic, we need to have a background of a classical set theory. We all know what is a set. A set is a collection of any well-defined objects. So you can say an object when it belongs to a set, we call it as an element of a set or a member of that particular set. As a definition from the textbook, you can see a set is a collection of distinct elements or members without repetition and without ordering. For example, we have given here a set of particles, that is electron, proton, and neutron. And since the set is defined by its member without regard to ordering or repetitions, you can say that these elements that are shown in the set is identical to the set proton, neutron, electron, or any other kind of set that is shown here with repetitions. Some examples of, you can see sets are given here, like a set ABCD described below with its members. A is equal to Jack, Jill, Hill, Pail, Water, etc. You can see how they are enclosed in brackets and separated by commas. And these are some set of examples like that. So a set T is basically, you can see a set of all days of a week. Okay, so each one is a member of that particular set. You can write it in an alternative way as D is the value X, such that X is a day of the week. Few other such examples are also given here, like given a set T with the value X such that X is an integer and it is between -1 and +1. X such that X is a prime number, and so on. So these are examples of set, and we already know the basics of set from our previous classes. Okay, now coming to the definition of a classical set, or also known as a crisp set. You can see a classical set theory is built on the fundamental concept of the set theory itself, where each individual that you take from a set is either a member of a set or not a member of a set. You have a crisp boundary on whether it becomes a member or it's a non-member. Okay, so that is why we have a precise and a clear boundary to that. So you can look at this definition here. A classical set is defined by crisp boundaries, and there is no uncertainty or vagueness in the prescription or the location of the boundaries of the set. Hence, a classical set is also known as a crisp set. So what we're going to learn is a fuzzy set, that is the opposite of what we are learning here. So in order to define a fuzzy also, we need to know what is the basic concept of a universe of discourse. You can say basically it is the entire collection of things or collection of objects that have the same characteristics. So all the elements in the universe X, where X is denoted by capital X, will be denoted, the element inside capital X will be denoted by small x. So the usual letter that is followed for universe of discourse is usually capital X, or in some textbooks you can find capital U also. So some examples of universes are all the set of real elements, all the integers, clock speeds of computer CPU. It can have different kinds of values, but of the same type. So if we define a crisp set, it will be something like this. Let X be a universe of discourse. Let X be a universe of discourse, that is a universal set, and its elements is denoted by small x. So in classical set theory, how we define is we will have to define a characteristic function of a set A. Say suppose you have a crisp set A of that comes under the universe of discourse capital X, and we have a function f of a or mu of a. You can call any name for the function. So f of a for a element small x, that is called as a characteristics function of a. Now, how we define it, it is such that x belongs to the set of values, you can say 0 or 1, where what it means is f of a of x is 1 if small x belongs to the set A. It is 0 if x does not belong to the set A. The simple meaning of this is that if x is a member of A, then the value returned by the function will be 1. If x is not a member of A, then the value returned by it will be 0. So what happens here is this set maps the universe X to two sets of elements, that is either 0 or 1. So if it is a member, it is 1. If it is not a member or an element, not an element, then you call it as a, then the answer it returns is a 0. So all the operations on a classical set, we know that is union, intersection, complement. These are all the simple things that you learned earlier, but still we'll go through it once again. So A union B is given that X such that X belongs to A or X belongs to the set B. That is, it either belongs to the set A or it belongs to the set B. So if either one of them is true, then you say it is a union. Intersection denoted by the intersection symbol we have learned earlier. So it where such that X belongs to A and X belongs to B. It should belong to both set A as well as set B. Complement, you call it as an element as a complement when X does not belong to A, but it belongs to the set of universe of discourse. That is a universal set, capital X. Difference is when X belongs to A, but X does not belong to B, belong to the set B. It's also denoted by A minus B. You can understand it better with the help of these Venn diagrams. You can show it in a circle manner also. So this is just an example. A union of set A and B is given by, you can see the shaded portion given here. Intersection of set A and B is given by the shaded portion that is over here. Complement is where it does not belong to the set A. And the difference is that contains the value that is contained in A but not in B, or the intersection of A and B. Properties of classical set, I'm not going into the detail. These are basic properties. Idempotency, that is A union A gives A intersection A gives A. It's a commutative property when you say A union B is equal to B union A. Similarly, A intersection B gives is equal to B intersection A, and so on. Associative also we know where a combination of like B union C and the whole union A, you can say, is equal to A union B the whole union C. Similarly, intersection. Distributive, when you can say it's like this: A union B intersection C gives A union B intersection A union C. De Morgan's law, we take the complement of the union of two sets, that is the intersection of their complements. So if you have A union B, the whole complement is same as A complement intersection B complement. Similarly, A intersection B complement is same as A complement union B complement. That is, it is basically the complement of union and the complement of intersection. Basically, these laws state that the elements not in A union B are exactly the elements that are not in A and not in B. And whereas the other one states the elements that are not in A intersection B are the elements that are either not in A or not in B. That is the basic idea. Then we have identity, involution, law of excluded middle, law of contradiction, universal complement, absorption, and so on. Absorption is A union, A intersection B gives A. So there are proofs for this, but this is not so important. Just for the sake of understanding, you can read through it. When we learn fuzzy set, we'll go more into detail. So coming on to fuzziness, we all know that the traditional logic is basically looking at, or you can say the Boolean logic kind of thing, where you look at only zeros and ones or true and false. So you can see the traditional empirism is we are thinking of what we experience or what we observe. Only that can be accepted as the truth, isn't it? So what exists and what does not, what causes something, what does not. So these are the basic foundations of science. But however, since early Greeks, people have found that they understood that the world is in black and white, and hence the concept of fuzziness came into existence. There's a paradox, a famous paradox, which says if I remove one sand grain from a pile, it's still a pile. Because you know, a pile is basically a heap of sand, where if you remove one grain of sand, it does not become, it's still a pile. So but if you keep on doing this, at some point, all the sand grains will be removed, and eventually it will not be a heap or a pile, right? So, but we do not know exactly where that point is. Depends on the height of the heap or the number of sand grains in the pile. So, so there is a point or there is a limit where the last grain will not be a part of the pile. So you be simple sand grain. So experts basically rely on common sense, that is the human nature, when they solve problems. So how can we represent expert knowledge that uses vague and ambiguous terms when it comes to a computer? Because when you talk of human common sense kind of thing, we know how to evaluate uh, the difference between true and false or the values that come between this. But fuzzy logic is basically not a logic that is fuzzy, but it's logic that is used to describe the term fuzziness. So you cannot say because the fuzzy is basically a negative term, you can say. So that is why the scientists were not in support of when fuzzy logic came into existence. So fuzzy logic is a theory of fuzzy sets, and the fuzzy sets are nothing but that describes what is vagueness. So fuzzy logic is based on the idea that all things have a degree concept, an admit of degree. Like if you take any example, like temperature, height, speed, distance, beauty, everything. Like I simply say, Tom is a tall guy, or Tom is a very tall guy. The motor is running hot. When I say the motor is running hot, what is the degree of hotness here? Is it really hot or it's slightly hot, and so on? So many decision making tasks, you can say, are very complex to be understood quantitatively. So we need to have some knowledge to understand what is that impreciseness there. So fuzzy set theory resembles human reasoning, that how we think the same way in its use of approximate information and uncertainty to generate decisions. So based on this uncertainty or vagueness, we have to come to a particular decision, right? So we have to have a concept of the same human reasoning kind of thing. So it was specifically designed to mathematically represent uncertainty and vagueness and provide formalized tools for dealing with imprecision intrinsic to many problems. Mm, an example of, you can see, that is if you want to draw a line between members of a class and non-member of a particular set. Say we are talking of tallness, right? So if Tom is tall because his height is 181 centimeter. So suppose I drew a line at 180 centimeter and we bring another person, say David, who is 179 centimeter. So would we classify him as small? You can imagine that 180 is a particular, uh, you can see, if I say 180 is a measurement of tallness, so the person beyond 180 we classify as tall, and the person less than 180 we classify as small. So is that the proper way of doing it? So we should, so exactly classifying as true or false or 0 or 1 will not work in a real world engineering or decision kind of problem scenarios. So fuzzy logic reflects how people think. So human reasoning, that is what I said. So bringing it into AI and machine learning and all is a very common thing today. So coming on to fuzzy logic, just the definition, it's a method of reasoning that resembles human reasoning and how we think and how we make a decision. It involves all the possibilities between yes and no. So fuzzy logic systems, you can see, is something that takes as input something that is fuzzy, like incomplete things or ambiguous things, inaccurate things will be the inputs, but we will have a definite output. So when you talk of a system which applies fuzzy logic, you call it as a fuzzy logic system. So you can see here, is it cold? Yes and no are the Boolean logic all we all know. So, but when it comes to fuzzy logic, we can classify it by using things like very much, little, very less, etc. So with that, we associate a value. Say instead of 1 and 0, I put a 0.9 for very much, a 0.25 for little. And when it is very less, you can say it is 0.1. So it's basically a value between 0 and 1. So conventional logic block that a computer understands uh, takes precise input and gives a definite output like a yes or no. But fuzzy logic that was invented by this person, Zadeh, he observed that unlike computers, humans have a different range of possibilities between yes and no. Like yes and no can itself vary from certainly yes, possibly yes, cannot say, possibly no, and certainly no. So where do we apply all this? You can see how it can be implemented. It can be implemented in systems with different sizes and capabilities, such as microcontrollers, large networked or workstation-based systems. It can be implemented in both hardware and software or a combination of both. Looking at the history, the concept was multi-value logic was actually introduced in the 1930s by Jan, a Polish philosopher. But later on, his famous paper, 1965, Zadeh published his famous paper, Fuzzy Z, which actually introduced a lot of contradiction, but was eventually accepted, you can say, where the fuzzy terms were introduced. So fuzzy logic is a set of mathematical principles for knowledge-based representation based on degrees of membership. Earlier you saw how um, this was classified. Is it cold? Very much, little, very less. You can see these are all degrees of membership. So based on this degrees of membership, fuzzy logic knowledge representation can be shown. So unlike a two-valued Boolean system, fuzzy logic is multi-valued. You can see in this figure, Boolean logic, you have either black and white, but when it comes to multi-valued, you can see a range of shade from white to black. So that is how they have depicted it. An example of the previous example that we looked into based on the height. So the fuzzy set. Now we're going to look at what is fuzzy set. So the concept of set is basically fundamental to mathematics. We already know that. So when we say car, it indicates a set of cars. So we have a set of cars out of which we're picking up one car. So we need to know the car type and all. The classic example is this tall men. So the elements of the fuzzy set tall men, they're all men, but their degrees of membership vary based on their height. You can look at this table here where Chris has a height of 208, Bill has a height of 155, etc. So if it was a crisp set, we would have, when I gave you what to say, a bar of 180 centimeter for classification to the tall category. And you can see here, if you have a height of greater than 180, you in the crisp set, you will be having a value of 1, showing that the degree of membership is the most, what to say, the highest one. So whereas when all the other values have a degree of 0, so you can see it has a two-valued that is a Boolean valued thing, either 1 or 0. There's no degree there basically. It's either 1 or 0. But when it comes to fuzzy, you can see the height. You can, if it is too high, you classify it to the category 1, and if it's too low, you classify it to the category 0. And the rest of the values in between will have a degree of membership indicating how close it is to the bar that we have set. So if you want to represent it using a graph, it will look something like this. So the x-axis represents the universe of discourse, the capital X. That means all possible values applicable to a chosen variable. So in our case, the variable is the man's height, right? So according to this representation, the universe of the men's height consists of all the tall men. And the y-axis, you can see here, it shows the membership value of the fuzzy set. The membership value is the degree of membership. Okay. So you can see the height values are exact deviation. You can see here, just show that when it is 180 is either, you can see here the membership value is 0 for all values less than 180. But whereas for all values greater than 180, it comes to 1. There's no other value in crisp set. But in fuzzy, that exact barrier is gone. And you can see here, you're gradually progressing like this to show that all the values below 180 will have some membership degree, like varying from 0 to maybe 0.5 or something, or point something like that. Above 0.6, you can say. And all the other values still 1. When the height of the person becomes 210, it comes to a value of approximate degree of membership becomes 1. Another example of a crisp set and a fuzzy set, showing a glass filled with water. So is the water full? I think there's some grammar mistake here. Please ignore that. Is the water full? It is 0 here, but whereas it is 1 here. It is half filled here, but there is no solution for that in a crisp set. But when it comes to a fuzzy set, you can see 0.5, 0.8, and so on. You have different degrees of membership. So coming on to the formal definition of a fuzzy set, we saw earlier how a crisp set looks like, right? Like you have a membership function or a characteristic function f of a such that the universe of discourse has the value 1, 0, and 0 and 1. And if it is a 1, that means x is a member of a. If it is a 0, that means x is not a member of a. That is the basic idea. Now, in a fuzzy set, you can see what happens. The fuzzy set A of universe X is defined by a function. We change the function name from f to mu. So mu of A for the element of x small x, such that the membership function of set A is given by, you can see the square bracket 0, comma 1. Okay, it's in the interval 0, comma 1, where mu of A of x is 1 if x is totally in A, and it is 0 if x is not in A. But if it is between 0 and 1, that means x is partly in A, or you can say a partial membership inside A. So that is how you define a membership function of a fuzzy set. So this allows for possible choices, you can say. So for any element x of the universe capital X, the membership function mu of A equals to the degree to which the x is an element of the set A. If the value is between 0 and 1, you can say it represents the degree of membership, also called the membership value. The degree of membership or membership value, both are the same thing for the element small x in the set A. And you can see here a simple boundary showing what is a crisp set and what is a fuzzy set boundary. We can go beyond the exact boundary indicating in the universe of discourse itself, of course, showing a fuzzy boundary. So once we determine the membership function, In our tall men example, you can see, suppose you have fuzzy sets of tall, short, and average men. The universe of discourse, you can see it consists of these three sets. As you can see, a man who is 184 centimeter tall is a member of average set also with a degree of membership of 0.1. And at the same time, he is also a member of the tall set with a degree of membership of 0.4. You can see when we draw a graph or a chart graph like this, the crisp set will have, you can see, a straight bars or blocks of information like this. But when it comes to fuzzy sets, you can see he will have some share of membership in the all the maybe in either of the two sets. Say, for example, 184 is the value we took, right? So when 184 is the value, you can see he may fall in this category and he may also fall in this category. And he may fall in both the categories, average as well as tall. Got it? So that is what is written here. He has a degree of 0.4, membership of 0.4 in the tall men set, and a degree of membership of 0.1 in the average set. So this is how we can indicate it using a figure. And eventually when you learn how to plot all this, you'll understand that the graphs have different shapes like this. I'll teach you all that in the next video. Okay, so typical functions that you can use to represent the fuzzy set are sigmoid, Gaussian, pi. We'll look into that later. So you can see here, basically a crisp set will be it's a subset of a fuzzy set like this. And when you're describing fuzziness, instead of a block like bar that falls, you'll always have you can see the fuzziness is indicated by the gray shaded area, the entire gray shaded area, including the black. So this is how in most of the applications, this is how it will look like. Now, looking at the definition of how a fuzzy set can be written into, this is how a fuzzy set F on a given universe of discourse capital X or capital U is defined as a collection of ordered pairs. It's very important to know this, that you have a set of ordered pairs X, comma, mu of F of X, mu F of X. So if F is a fuzzy set, they have given the name of the set here as F and the universe of discourse as U. Then you can see for all elements that belong to the set F, each ordered pair is written with it the value that contains in the set and the membership, degree of membership of that particular value. You write it as an ordered pair like this. So where X belongs to U, for all X that is a subset, you can say subset of U, and the membership functions falls between 0 and 1. So that is how we write a fuzzy set. Now there are different notations. You can see each pair that we are written here, that is X comma mu of F, is basically known as a singleton. So you can see the values are usually restricted to 0 and or 1. So apart from that, this is one way of writing it. Another way of writing is you can also put a sigma. You can also put a capital U like for the union. Okay. Both the ways also you can write. Now, while writing like that, we have to write it in this way, where the membership function mu of F, you can write the divided symbol by X. So it's a divided symbol, but it does not actually mean division. It is just a notation. So you can write, say, for example, if you have a fuzziness value of 0.1, you can write it as 0.1 by, for the member. Suppose the member value is 2. For a value 2, the fuzziness membership value was 0.1. So you write it as 0.1 by 2 plus the membership value of the next value. Say the next value is 3 and its membership function degree of membership is 0.4, then we write 0.4 and so on. So you can write it this way. So basically two ways of writing. I'll give into the detail in the next video. So the summation is basically union over all the singletons. You're just writing. It's not basically the arithmetic sum like 2 plus 3 or something like that. It's just a notation showing that it's a some union of all the things that are there in uh, all the elements that are there in the set. Okay. Now, suppose these are applicable for discrete sets. So suppose you have a continuous set, then the sigma value will be replaced by a integral sign. So another example of how we can understand this is a fuzzy set and fuzzy membership. Say you have 5 students A, B, C, D, E who scored marks 55, 35, 60, 85, and 75 out of 100 respectively in maths. So the students constitute the universe of discourse, the capital X or the capital U, A, B, C, D, E. These are the members of the entire set. And the fuzzy set M of students who are good in mathematics is defined on U with the help of the following membership function. You can see the membership function is given here. We define it in such a way that if a student's mark is less than 40, then we say the membership function counts to 0. If the value is between 40 and 80, we say x minus 40 divided by 40. So we have given a benchmark, you can say like 40, uh, which shows that he has a degree of membership. So if it's less than 40, that means maybe he failed, so it's 0. And if it's greater than 80, that means he has a membership he has full membership into that is it is 1. Okay. So this way we have to find out the membership of all. So what we do here is we can write it in pairs like this. So suppose that you have a value less than 40. Say for the value B, you can see that he got a mark of 35. So that is less than 40, right? So the membership value of value B is basically the membership value is 0 like this. Similarly, you have to find out for value A, C, D, and E. So I just pointed out the simplest one first. B has a membership value of 0. So similarly for A, we have to find out because we have to calculate. So the value of for the student A, the mark is 55. The mark is 55. So you write 55 minus 40 divided by 40, you get a value in some point. So you write a comma, say you got some 3 point something you get. So you write 0.3 like this. Okay. So this way we find out the membership function for each of the student. And you can see in the next slide the values. So this is how the values come in. Just delete the older. So you can see here, A has a value of 0.375, C has a value of 0.5, D has a value of 1.0 and E has a value of 0.8575. And you can see B has been excluded from the set Y because the membership is 0. Okay. So you can see here the membership value of each of the values that are applicable in the subset M is given here. And you can denote it in this way, or you can also denote it in this way. Both are correct or equivalently. This is the second option that I showed you earlier. That is, you can have a summation of, this one. You can have a summation of the membership value divided by the value itself. Either you can denote it this way or you can denote it this way. So both are correct. Now plotting a graph for this, you can see that this is how it looks like. So for all the values less than 40 will be 0. It will be 0 like this. And all the values between 40 and greater than 80, you can have a value of, say, for 55, a person, if 0.375. And for C, you got a value of 0.5 and so on. For D, you got a value of 1. For E, and for E, you got a value of 0.87. So it depends on the mark. 55, 60, 85, and 75. 85 is above 80, so that is why we got a 1 there. So A was 55, C was 60, and E was 75. Okay, so that is all.